Hello everyone, I'm pleased to have the opportunity to talk at this meeting. Now, I would like to share our work, FedCav contribution-aware model aggregation on distributed heterogeneous data in federated learning. We have 5 parts in this presentation: background, observation, and problem statement, our solution, experiments, and conclusion. Okay, let's begin the first part. With the development of AI, the data became more and more important. However, there are 2 important bottlenecks limiting the development. One is the data privacy problem. More and more people concerned about their personal data privacy, for it's sensitive to their personality. Many countries have launched laws about data privacy, such as GDPR in Europe. Another is the data island phenomenon. The data in each party does not share with each other. This causes the limitation in data usage, especially in distributed systems. The influence of these 2 bottlenecks is significant. The emerging federated learning allows multiple distributed devices to corporately train models in parallel, with the raw data retained locally, which preserves data privacy. Compared with the traditional machine learning, federated learning builds a good performance global model without exposing the raw data. As shown in the slides, we demonstrated a typical federated learning process based on the widely adopted Fed average for aggregation. As shown, local training is performed using the latest global model, where a new global model is attained by taking the average of all the locally trained models. However, the Fed average is criticized to have degraded performance when giving heterogeneous training data in practice. Generally, the data on clients are non-independent or identical, non-ID, and class imbalanced. Global non-ID represents the difference between each client. Local class imbalanced means the number of each class data should be different. Some class might have more instances or SAMs, some only have few. We found 2 problems both in our analysis and the following experiments. There are slow convergence and low training performance. In this part, we conclude and analyze the data statistical heterogeneous and investigate the influence of data heterogeneous on model performance in federated learning. We demonstrated the experiments. We used the digital handwriting dataset MNIST and a basic CNN called LeanNet5. According to the analysis before, we built 3 different types of data distribution: ID and balanced, non-ID and balanced, and non-ID and imbalanced. ID and balanced, global ID and local class balanced. Most research is based on this setting. Non-ID and balanced, global non-ID but the local data is class balanced. Non-ID and class imbalanced, the setting is more similar in real world. In this experiment, we set a parameter sigma to control how imbalanced the local data is. As shown, we can observe that there are 2 main features. One is slow convergence. With the balanced data, Fed average only needs 5 to 10 communication rounds, but with the imbalanced data, Fed average needs more than 20 or 35 communication rounds. Another is the low training performance. With the balanced data, Fed average can get near 95% classification accuracy, but with the imbalanced data, the accuracy ranges from 80% to 93%. And from the curve, we can see that they are more unstable than the balanced one. In summary, we can conclude that the experiments in observation indicate the heterogeneous data will cause the slow convergence and low training performance. The reason might be the Fed average gives more weight on this large data. The data with small samples need more time for global model to learn. In other words, Fed average considers that the data with small samples are more valuable than small size data. However, in reality, the data with small samples do not represent they carry more information. For example, when using Gboard to typing, the word source is not as regular as the word me, and the word source is more valuable than me, for the source indicates dangerous. The animal pictures. The pictures of pandas are more valuable than the pictures of cats. Cats are common and can see everywhere. The photo can easily get, but the pandas not. We first show our solution called FedCav. The framework contains two parts. One is contribution-aware model aggregation. Consider the malicious attack might use our methods to attack. We design a simple but effective attack mechanism. The workflow of FedCav can show in the picture. At the beginning of federated learning training process, the cloned server initializes the global model and deploys it to the clients. The clients download the global model and train the model based on their local data. At the same time, contribute a value called inference loss, which is a global model loss value in each client. After finished training, the clients upload their updates to the server and aggregate these updates by using contribution-aware aggregation methods. Meanwhile, the server needs to recognize whether the update is abnormal. By comparing the inference loss with historical values, each client reports the states, and the final decision is consistent with the majority. Once an abnormal update occurs, the server will reverse the global model to catch the one. This part is the detail about the contribution-aware aggregation methods. In our analysis, the clients make more contribution to the model improvement should have more weights in aggregation. So, how to measure the contribution at the same time, preserving the privacy? We design a variable called inference loss, which is a loss function value of global model on client's local data. If the inference loss is large, this means the global model needs to pay more attention to the local data. As shown in the slides, in the client side, the clients do not only need to perform local training, but also need to calculate the extra value. In the server side, the server will aggregate the local model updates weighted by softmax or the inference loss. The reason why to use softmax is the softmax can set up the mechanism. So clients with high inference loss can get more attention compared with the linear function. At the same time, we found it's necessary to clip the inference loss. We want to scale up the contribution of high inference loss clients, but it should be limited by a certain range. So we use the widely used methods to clip the inference loss. The model replacement attack is one of the most common attacks in federated learning. It is simple and low cost. The attack might use the contribution-aware aggregation method to perform the model replacement attack. The detail of how the model replacement attack is shown in the slides. Facing this attack, we need to design a detector mechanism in our framework. We reuse the inference loss uploaded from clients. Comparing the inference loss with the historical value, if the value increases greatly, the clients report abnormal. The final decision is consistent with the majority shown in these cases. Once an abnormal update is detected out, the server will reverse the global model to catch the one, which greatly reduces the time to fix the point in the model. To better get the performance of our framework, we have some experiments. First, I will introduce the basic setting in our experiments. We use three widely used datasets. The cases of the datasets and corresponding training models are shown in the table. We first evaluate the performance of contribution-aware aggregation methods. We set three different heterogeneous data distribution networks. The parameter sigma have the same meaning with the above experiments. We can get a result that the performance is higher than other baselines. Then, according to our analysis in the heterogeneous state, the data is dynamically changing, so we simulate a dynamically changing network. At each communication round, there are some fresh data collected by the clients, and the fresh data size is controlled by the parameter alpha. We can see that if there is a fresh data, the FedCav only needs few communication rounds to get a certain accuracy. In this part, we average the impact of the clip shrinkage. We compare the two methods. One is FedCav use clip shrinkage, another is not. We can see that the FedCav without clip shrinkage occurs great up and down. It's not stable for us to use these methods without clip shrinkage. In this part, we simulate the model replacement attack. We first compare the performance of FedAverage and FedCav without detection. The results are shown in the pictures. We can see that the FedCav without detection still have a little superiority than the FedAverage. This is because the FedCav can make the client's contribution more after attack, so it can recover from the attack quickly. At last, we evaluate the detector mechanism. The performance, we perform 3 different strengths of attacks. The malicious model is trained by 20%, 50%, and 80% label points in the malicious model. We found that our framework can detect out the abnormal updates and reverse the global model to a healthy one. Ultimately, the main problem of our paper wants to solve is the heterogeneous state problem in federated learning. In observation, we found that heterogeneous state will cause the slow convergence and low training accuracy. We propose the FedCav framework. In FedCav, we design the contribution-aware model aggregation, and we also consider the malicious attack. In our evolution, our methods have better performance than baselines, near 2.4%, and needs less communication runs to achieve convergence, near 34%. Okay, that's all my viewpoints. Thank you very much for kind attention. Any questions are welcome if I don't explain something clearly.